Mr. LaBeouf here for the 7th graders to continue talking about negative exponents. We've already established in previous videos that when you raise a non-zero number to the 0 power, you get 1. For example, 4 to the 0 power is 1. And we've established that raising a non-zero number to the -1 power gives you the reciprocal of that number. So 3 to the -1 is 1/3. And it works for fractions as well. As you know, the reciprocal of 3/4 is 4/3. If you have 3/4 in parentheses raised to the -1 power, it's 4/3, the reciprocal. But now in this video, we're going to have to be able to deal with raising numbers to negative powers other than -1, like -2, -3, and so on. This video will not get into fractional exponents yet. That's sort of the last piece to the puzzle, which we may or may not get to as 7th graders. But before we get to raising numbers to negative integers other than -1, let's look at a result of being able to raise a number to the -1 power. Here I have a couple of fractions, 3/4 and 9/7. These fractions can be written in a way without a fraction bar. The fraction bar, after all, is just a symbol. It has a certain meaning. The denominator tells us to divide the unit length from 0 to 1 into that many equally sized pieces, and then the numerator tells us which one we're interested in. So it's just a symbol, and exponents are symbols as well. So let's follow the conclusion to a conclusion. Follow the logical consequences of this -1 power. 3/4, of course, is 3 times 1/4. And the 1/4 can be written as 4 to the -1. 4 to the -1 is 1/4. So 3 times 4 to the -1 is the same as 3 times 1/4, which is 3/4. And in a similar way, 9/7 can be thought of as 9 times 1/7. 1/7 is 7 to the -1. So here's 9/7 without a fraction bar, but it still is 9/7. So that's just a little consequence of the -1 power. We know that 3 to the -1 is 1/3. Well, how about 3 to the -2, 3 to the -3, 3 to the -4, and so on? Well, at this point, we're going to rely on rule number 2. Rule number 2 tells us that when you have x to the m power, and then you raise that to the n power, you multiply the exponents. This becomes x to the m times n. This is rule number 2. Well, to evaluate 3 to the -2, let's think of it this way. Let's think of it as 3 to the 2 power raised to the -1. Now we can do that because of rule number 2. We would multiply the exponents here. 2 times -1 is -2. Well, 3 to the 2 power we know is 9. So this is 9 to the -1, which is the reciprocal of 9, or 1/9. So 3 to the -2 is 1/9. You could probably figure the other ones out now pretty easily. 3 to the -3, we'll think of it as 3 to the 3 raised to the -1 power. This should be continuing to give you the idea that these rules of exponents are the way they are because they work. That's all. It's as simple as that. 3 to the 3rd power is 27. So we have 27 to the -1 power, which is the reciprocal of 27, or 1/27. And 3 to the -4 can be thought of as 3 to the 4th raised to the -1 power, or 81 to the -1 power, or 1/81. So this pretty much covers how we raise a whole number to a negative integer power. I'd like to now give you a very cool result of some of the things that we've learned just this week, and that is, how about considering powers of 10? and particularly the powers of 10 that are less than 10 to the 1, 10 to the 0, 10 to the negative 1, 10 to the negative 2, and so on. Well, 10 to the negative 2, as we saw with raising 3 to a negative power, that can be thought of as 10 squared raised to the negative 1 power, because rule number 2 would tell us to multiply the exponents, and 2 times negative 1 is negative 2. And 10 to the negative 3 can be thought of as 10 to the third raised to the negative 1. 10 to the negative fourth would be 10 to the fourth raised to the negative 1. So we have 100 to the negative 1. 10 squared is 100. 100 to the negative 1 is 1 over 100. 10 to the third is 1,000. 1,000 to the negative 1 is 1 over 1,000. And 10 to the negative 4 can be thought of as 10 to the fourth to the negative 1. 10 to the fourth is 10,000. Raising 10,000 to the negative 1, taking its reciprocal, we get 1 over 10,000. So just let that sink in a little bit. By the way, this could also have been written, the 10 to the negative 2 could have been written as 1 over 10 to the 2. This 1 over 100 is 1 over 10 to the 2. We could have just kept the 10 to the 2 rather than representing it as 100. We could have kept the 10 to the 2 and written 10 to the 2 raised to the negative 1 as 1 over 10 to the 2. 1 over 1,000 is 1 over 10 to the third. 1 over 10,000 would be 1 over 10 to the fourth. You could do it either way. Now, I've created a number up here, kind of a nice number. The nine digits in order, 1, 2, 3, 4, 5, 6, 7, 8, 9. I've decided to put a decimal point here. And here's a really cool result of the things that we've learned. We know already, of course, that we know the powers of 10, the place values. Our number system is one that depends on place value. This 1 here has a much different value than if a 1 were here. This is really 1 times 10,000. It's in the 10,000s place. Let's represent the places by powers of 10 that we're already familiar with. The 4 is in the tens place. I'm going to put a 10 under the 4 because the 4 is in the tens place. It's really 4 times 10, or 40. The 3 is in the hundreds place. I'm going to put a 10 to the 2 there. You should know by now, you should be very comfortable with the fact that 100 is 10 to the 2. The 3 is in the hundreds place, which is the 10 to the 2 place. The 2 is in the thousands place. That's 10 to the 3. And by the way, the powers of 10 have a 1 followed by that many zeros. 10 to the third is a 1 followed by 3 zeros. 10 to the 17th, I don't know what it is off the top of my head, but what a name for it is, but it's 10 to the 17th is a 1 followed by 17 zeros. And the 1 is in the 10,000s place, which is 10 to the 4th. So you certainly see a pattern here. These, as we go to the left, these powers of 10 are increasing by 1. Well, the 4 is in the tens place. We saw earlier that, as we suspected, 10 can be thought of as 10 to the 1. So here we have 4, 3, 2, 1 as we go from left to right. And we know that the ones place now, up until now, you've always called it simply the ones place. But now you can think of it as one of the powers of 10 place. It's 10 to the 0. The ones place is 10 to the 0. Okay, so the pattern left to right continues, 4, 3, 2, 1, 0, and it continues forever because the tenths place, the 6 here, is really 6 times 1/10, and 1/10 is 10 to the negative 1 power. The 7 is in the hundredths place. These places to the right of the decimal point, of course, when we name them, they end in THS. This 7 is in the hundredths place. That's 10 to the negative 2. The 8 is in the thousandths place. We've already done that down here. The 8 is in the thousandths place. That's 10 to the negative 3. And the 9 is in the 10,000ths place, or 10 to the negative 4. So look at that beautiful result. Math is all about consistency. Everything hangs together in one nice, easy story. 4, 3, 2, 1, 0, negative 1, negative 2, negative 3, negative 4. And that pattern continues forever, whether you're going to the left. The next place over here would be 10 to the 5th. And if you go to the right here, the next place would be 10 to the negative 5th. Along the same lines of what we just looked at with the place values, including the negative powers of 10, we can write what's called a decimal expansion now of any number in decimal form. This number, 501.329, or 501 and 329 thousandths, can be thought of this way. It's 5 times 10 squared, that's 500, plus 0 times 10 to the 1. We could leave that out, of course, because 0 times anything is 0, but just to deal with each of these places, plus 1 times 10 to the 0. Now 10 to the 0 is 1, so 1 times 1. This is just 1. That's all. That's what the value of this number is. It's simply 1. But in terms of these place values using powers of 10, once again we see that there's going to be a descending order of the exponent. 2, 1, 0. Now we get to the 3, and we have to add to what we already have. We have to add 3 times 1/10, or 3 times 10 to the negative 1. 3 times 10 to the negative 1. Plus 2 times 10 to the negative 2. And finally, plus 9 times 10 to the negative 3. This is called the decimal expansion of this number. And now that we know about 10 to the 0 power and 10 to the negative powers, we can do a decimal expansion for any number. I want to now cover a topic that I wouldn't necessarily mention at this time, except for the fact that you have some assignments in IXL this week that give you these kinds of problems, which are not my favorites. I don't think that there's much value in them going forward, but I want you to be able to succeed with them on the IXL assignment. I think I'll start this little topic with the observation that when you take a number A that's not 0, any number that's not 0, and you put it underneath a 1 over A, well, that's the reciprocal of A. If you multiply 1 over A times A, you get 1. So 1 over A is the reciprocal of A. And this works for any number other than 0. It works for fractions. If you take the fraction 3/4 and you put it underneath a 1 like that, well, this symbolism here means the reciprocal of 3/4. This is equal to 4/3. If you want to, you can think of this as a division. 1 divided by 3/4. Math always hangs together consistently. You've been taught that this can be thought of as a division. So this is 1 divided by 3/4, and we know that we can flip and multiply. Flip the 3/4 and multiply 1 by 4/3 to get 4/3. So 1 over 3/4 is 4/3. Likewise, if we had 3/4 to the negative 1, these are two ways to represent the reciprocal of 3/4. Either way. And I mention this now because in these assignments that I think you're going to run across this week, you're going to have some problems to deal with, some things to evaluate where you have a negative exponent in the denominator. to me, it doesn't make much sense. You know, as we saw before, if you have 3/4, you can write it like this. This makes sense to me. Being able to rewrite a fraction without a fraction bar, without apparently any denominator, although this 4 is in the denominator, even though it doesn't appear to be because of the exponent of -1. But what about this? This is the kind of thing that you're going to get, you know, in not only in IXL, but other math books have them as well. And they've always kind of frustrated me because I've never seen great value in them. But 3 over 4 to the -1 can be thought of as 3 over 1/4. Right? 4 to the -1 is 1/4. 3 over 1/4, which is equivalent to 3 times 4. This is 3 times 4, or 12. 3 over 4 to the -1 is 12. Now, another way that you can think about negative exponents is put the number in reverse position between numerator and denominator, and then make the exponent positive. So in other words, 4 to the -1 in the denominator is the same as 4 to the 1 in the numerator. This can come up here as 4 to the 1, and 3 times 4 is 12. And that's a way that you can always look at negative exponents. Change position between numerator and denominator. Even if you have what I consider a normal kind of situation, you've got 5 times 6 to the -2. Well, there doesn't appear to be any denominator here. This could be thought of as 5 times 6 to the -2 over 1. But to evaluate this, you can take the 6 to the -2, move it down into the denominator, but then make this exponent positive. So this becomes 5 over 6 to the 2, or 5 over 36. Change position between numerator and denominator, and then change the sign of the exponent from negative to positive. That should work. Sometimes they give you really crazy things, like 3 to the -2 over 4 to the -3. Something crazy like that. Well, 3 to the -2 is equivalent to 3 to the 2 in the denominator. And 4 to the -3 is equivalent to 4 to the 3rd in the numerator. That's how it works. 4 to the 3rd is 64. 3 squared is 9. So this crazy thing here, 3 to the -2 over 4 to the -3, is equivalent to 64/9. We'll leave it at that for now. Take care.